I'm John Cubali. I'm project director for SBE-CCC, and I'm really happy to welcome you guys and thank you for joining us for today's presentation, Applications of a New Measure of Non-Ignorable Selection Bias for Proportions to Survey Estimates of COVID-19 Vaccine Uptake and Pre-Election Polling with Dr. Brady West. And as I mentioned, today's presentation is brought to you guys by the Social Behavioral and Economic COVID Coordinating Center, or SBE-CCC, at ICPSR. For those of you that are not familiar with us, we're a center for communication and collaboration among NIH-funded projects undertaking social, behavioral, and economic research on COVID-19. We promote an innovative cross-disciplinary approach to COVID-19 research across the behavioral and social science community, multiple NIH award recipients, and the public. If you haven't already, we hope you'll take a moment to visit our website where you can join our mailing list to receive occasional updates from the Coordinating Center. So now with that, I'd like to introduce today's speaker. Dr. Brady West is a research professor in the Survey Methodology program located within the Survey Research Center at the Institute for Social Research at the University of Michigan, Ann Arbor. He earned his PhD from the Michigan Program in Survey and Data Science in 2011. His current research interests include the implications of measurement error and auxiliary variables and survey paradata for survey estimation, selection bias in surveys, responsive, adaptive survey design, interviewer effects, and multi-level regression models for clustered and longitudinal data. And with that, Brady, I will turn it over to you.
Okay, thanks, John, and thanks to the SBE-CCC for having me. Really happy to talk about this material today with you. And I do want to say right up front that just because we're a bit limited in terms of time, I've prepared two examples. I'm probably going to spend more time talking about the COVID-19 vaccine uptake example, and then you can see the R code to carry out these analyses up on the website at the link that Megan has provided. You can see that in the chat. So I'll try to wrap up by around 3:50 so that we have time for questions after the webinar has concluded here. So thanks again for the invitation. Happy to be here. Folks are welcome to email me at the email address you see here if you have any questions about using these measures or anything else related to the presentation today. Happy to take those questions if you shoot me an email. Okay, so as part of the materials, you'll see our markdown file. So I've prepared our code in the form of a markdown file that you can run and compile on your own. Just let me know if you'd like to carry out these examples and I can share the data with you. I'm going to walk through the examples. I'll make heavy use of tidyverse commands just so you're aware. I'll also highlight the necessary packages and functions that you would need in R to carry out these analyses. And again, please don't hesitate to follow up with me by email if you have any implementation questions after today's webinar is concluded. So what's the problem that I'm talking about? Folks have big data all over their lips these days. These big data are everywhere. They're inexpensive, but they often arise from non-probability samples. And that's a big deal in many different kind of domains of research. And these non-probability samples lack a statistical basis for making population inference. And so we have to turn to model-based approaches to make inference based on these types of samples. And individuals will often self-select into these samples. They might volunteer. They might hear about it from their friends. And unlike with probability samples, the researcher can't control the probability that an individual participates in one of these studies. This leads to concern about bias in the estimates that we're producing. And similar concerns exist for probability samples that have low response rates. And some response rates tend to be so low that it's hard to still call these samples actually probability samples. So this is just kind of a comic that some of you may have seen about this issue of selection bias and how, depending on who you have in a given sample, you could get a very biased estimate of something you're trying to study, depending on who self-selects. This is just saying that if you're at a stats conference, most people are going to say they've heard of selection bias, which makes sense. And even though that's exceedingly simple to think about, that's really what's happening with a lot of these non-probability samples. So the individuals or groups that enter a study differ systematically from the population that you're really interested in terms of an association or some outcome of interest. For probability sampling with a low level of non-response, this is usually not an issue, but this is potentially a very big issue for non-probability samples. And again, this can also be a problem for probability samples with very low response rates. So Don Rubin was the first to coin this kind of terminology that we can use in this context of survey non-response. An ignorable selection mechanism is one where the probability of participating in a given survey, and we'll extend that to be a study in general here in this case, depends on other observed characteristics. So selection into a sample can depend on something that we observe for all the units. Well-designed probability samples with complete rates of response have this property, and we can use weights to obtain estimates that are unbiased across repeated samples. A non-ignorable selection mechanism, on the other hand, is when the probability of participating in a study depends on unobserved characteristics, things you don't actually see and that you're trying to measure, but were otherwise unable to measure. And all non-probability samples potentially have this property. So we need to think about what estimation methods we can use in the presence of these non-ignorable mechanisms. So what we're going to learn and do today in the webinar, you can't know the truth from a non-probability sample, but you can conduct sensitivity analyses to see the sensitivity of your estimates to the assumptions that you're willing to make about the nature of the selection mechanism. And so the approach would be basically to say, how bad might it be, depending on the level of non-ignorability? And these sensitivity analyses and associated indices of bias, they're based statistically on something called a pattern mixture model. So that's the underlying model behind everything that we're going to be talking about in this particular webinar and these measures of selection bias. This model was really first used to develop measures of selection bias in the context of survey non-response, but we're going to generalize it to self-selecting into a given non-probability sample as part of a general selection process. So I'm going to briefly review the theory behind these indices of selection bias and spend hopefully most of the time walking through, again, examples of these calculations using R. So just to kind of provide some non-mathematical motivation for what we're talking about here, suppose you have a hypothetical non-probability sample of adults in the US, and you're trying to collect data on years of employment and age. So this is a volunteer opt-in online survey or something, again, where you have no control over the probability of selection. And in that non-probability sample, you see that the mean age is about 40 years, okay? However, you know, for example, from census data or other administrative data, that the true mean age in your population of US adults is actually 48 years. So there's evidence that your study is producing a negative bias in the estimated mean age. Your estimate is too low. Okay, you don't have any population information about years of employment. That's kind of your key survey variable that you're trying to measure. But if you know that age is positively correlated with years of employment, that suggests that you might also be underestimating the mean years employed using the data from your non-probability sample. So these indices that I'll be talking about take this idea a step further by assuming a specific model for the relationship between Z, some variable that's available for everybody, and in aggregate in the target population, Y, some variable that you're just measuring on your selected sample, and the probability of being in that non-probability sample in the first place. So the indices use all the information that's listed here to come up with reasonable estimates of bias that can be used in a sensitivity analysis to understand the implications of non-ignorable selection. So this is a high-level outline for the general approach to computing these measures of selection bias. We follow the following process in general. First of all, pick your outcome. Okay, so what's your dependent variable of interest in the non-probability sample, the selected sample that you're working with? So I'll spend most of the time talking about an indicator of whether you've received the COVID-19 vaccine, okay, as a measure of uptake. Okay, so pick your outcome. Second, find population-level covariate data. So identify a source of informative auxiliary variables in the population of interest that serve as good predictors of the outcome Y that you're interested in. So these variables must also be available in the microdata for your non-probability sample. Okay, so that's a key part here. At the population level, you only need aggregate statistics for these variables. You don't need microdata for the population. You just need aggregate statistics on these predictors Z. Okay, so that means means, variances, and covariances. You don't need the microdata. So you might get these aggregate statistics from census data or a large administrative database for your population or from a large probability sample. You can compute weighted estimates with very low standard error of these means, variances, and covariances based on a large probability sample from that target population. But we only need that information in aggregate. We just need the microdata on the predictors for your selected sample to make this stuff happen. Okay, step 3, compute what we call the proxy when computing these measures of selection bias. So using the data in your selected non-probability sample, compute what's called an auxiliary proxy for Y by regressing that key variable Y on the same auxiliary variable Z that are available in that aggregate population source. You fit a regression model of Y on those predictors using the data in your selected sample. And you can come up then with a prediction of what Y would be based on that combination of predictor variables. We call that an auxiliary proxy. Once you have this auxiliary proxy saved for the cases in the data set and the values on the variable of interest Y, then we apply that statistical model called a pattern mixture model. And this model allows the probability of selection into the non-probability sample to be a function of both Y, that would be the non-ignorable selection mechanism, right? Because we don't observe Y for the people who did not select into the sample, okay? And the model allows selection to depend on the auxiliary proxy that we computed based on all those predictors of Y. Because remember, we also have information on those predictors in aggregate at the population level. So we use that aggregate population information, the auxiliary proxy based on the selected sample, the value of Y, and the dependence of the probability of selection on either Y or the auxiliary proxy, okay, to formulate estimates of that bias. We draw on the auxiliary information for the full population on the sample, and we're going to talk about a parameter that lets you specify how much selection depends on your key variable of interest. In other words, the level of non-ignorable selection. Given all this information, then, we can create adjusted estimates. Okay, we can use our measures of selection bias to adjust an initial unweighted estimate of something like the proportion that have had the COVID vaccine, and obtain measures of uncertainty as well about those adjusted estimates. So we can use our measures of bias in our estimate of interest to go back and adjust our unweighted estimate and come up with a better estimate of what's actually happening in the population, allowing for non-ignorable selection. That's the key point. Okay. So our focus in the webinar is going to be on measures of selection bias for proportions. Measures have also been developed for estimates of means, for estimates of linear regression coefficients, for estimates of probit regression coefficients, but our focus today is going to be on measures of bias for estimates of proportions. So here's the basic idea when we're dealing with estimation of proportions in surveys. For a binary variable Y, so variable one for people who have some characteristic of interest, 0 for everybody else, we think about a latent variable framework. Okay, so we assume that there's some underlying normally distributed latent variable that we'll call U, which gives rise to the values on the binary variable Y that we actually observe in the survey. So in the classic probit regression model formulation, we observe Y as being equal to 1 when that underlying latent variable U, our kind of continuous latent propensity to have some characteristic, is greater than 0. Okay, so we think of that as a latent tendency to have Y being equal to 1. Okay, so the statistical model is based on that underlying normally distributed latent variable. We then create a proxy variable, like we talked about, fit a regression model to the observed data in the selected sample, a probit regression model specifically, compute our proxy variable, which are basically predicted values for the length function used for the probit. And we use that latent variable U in place of Y in the actual pattern mixture model. Okay, so we have our proxy, and then we have that underlying latent variable U. We also have to have the variance of that proxy in the non-selected sample, even if we're using non-Bayesian estimation. So I'm going to talk about a Bayesian estimation approach, but to compute these measures of bias for proportions, we need to have a way of computing the variance of that proxy variable for our non-selected sample. And one thing we could do is assume that the variance of that proxy variable is the same in our selected sample as it is in the non-selected sample. So I'll talk about how to go about that. So the basic approach for binary variables, in our non-probability sample, we have our binary variable of interest. Okay, we're calling that Y. We have those covariates or auxiliary variables for which we have aggregate population information from a probability sample or some other large data source for the population, okay? And then using that non-probability sample, we use those predictor variables Z to create an auxiliary proxy for Y, okay? Again, we introduce this normally distributed unobserved latent variable U. We get that auxiliary proxy from a probit regression model that we fit to our selected sample. Allows us to model the probability that Y is 1 as a function of those predictor variables Z for the selected sample. S is just a selection indicator saying it's 1 if you were selected in the non-probability sample. And then the proxy variable, which we'll call X, is the linear predictor from that probit regression model. So we take the estimated coefficients, we take the predictor variable Z, we form that linear combination that gives us the proxy variable X for each of the cases in our selected sample. Part of the evaluation of the effectiveness of these measures of bias is this proxy strength. So how correlated is that proxy variable with the actual binary outcome? And we use what's called a biserial correlation to gauge the strength of that auxiliary predictor as a correlate of our binary variable of interest. And the general methodology allows for other covariates that are independent of X and Y to figure into the selection process. And again, we're using S as an indicator for being selected for the non-probability sample. Okay. We then apply that proxy pattern mixture model to all the observed information. Remember that U is latent, so it's not actually observed for anyone. So we set the scale of that latent variable to 1 in the selected sample just to make sure that the model is identified. Furthermore, to make sure the model is identified, we make an assumption about selection. Okay. We write down this general function that defines the probability of being selected into the non-probability sample as a function of X, that latent variable U, and then these additional potential covariates called V, okay? Now, what's key to see in that selection function that defines the pattern mixture model is this parameter phi, okay? Phi dictates the dependence of selection on the dependent variable itself. You see here, that's U. So if phi is non-zero in this expression, that means that the probability of selection depends somewhat on the variable that we were trying to observe in the first place, a non-ignorable selection mechanism. If phi is equal to 0, that means selection depends only on X and potentially V, meaning that selection only depends on our observed information, which again is available in aggregate for the target population. We would call that ignorable selection, and we can model the probability of selection in that particular case. Phi at the other extreme being equal to 1 means that selection depends on the variable of interest only and not X. That means our selection is extremely non-ignorable. Generally, phi is probably going to range between 0 and 1. That means that selection depends on some combination of the auxiliary variables and the dependent variable of interest, which still is a level of non-ignorable selection. So in doing these kinds of analyses, we can make an assumption about what we think phi is. We might set it to 0.5, we might set it to 0.8, we might set it to 0.2. That's what allows for the sensitivity analysis, okay? We can toggle the value of phi and take a look at our estimates based on the pattern mixture model to see how sensitive the estimates are to the assumed level of dependence of selection on the variable of interest, which we're calling U here. And in a Bayesian approach to computing these measures, we start with random draws of phi from between 0 and 1. So we say, we don't know anything about phi. We're just going to take random draws of phi and look at the uncertainty in our estimates of bias based on those random draws. That's the idea here for doing this kind of sensitivity analysis. Okay, I'm not going to spend a lot of time on this slide. This is kind of showing the math for how we come up with these estimates of selection bias. But basically what you see in this equation here is a formula for the overall population mean. Okay, this is what we're trying to get at. And we're writing that as a function of the mean of Y in our selected sample, and then a model-based estimate of the mean of Y in the rest of the population, conditional on some selected value of phi. So prior work by Rebecca Andridge and Rod Little came up with this expression for the overall mean, in this case being a proportion of these components. And given that we can write the overall mean in this way, based on an estimate according to our pattern mixture model, okay, we can then use that information to turn around and write the difference between the mean of Y in our selected sample and what the true population mean should be. Okay, we just convert this formula to the difference between what's in our selected sample and what's in the actual population. Okay, and there's other expressions for the mean and variance of that latent variable U in the non-selected sample that we can compute. Key being that all of this information in computing these estimated parameters for the non-selected sample, we can recover those from data that were actually observed in the selected sample and values of phi. That's the beauty of this approach, is we can recover estimates of parameters for non-selected cases using information in the selected sample, okay, in addition to the parameters phi. And you can see the other papers that I'm citing here if you're more interested in the technical details. Okay, so again, long mathematical story short, you can write down this measure of unadjusted bias for a proportion as simply being the difference between the proportion in the selected non-probability sample and the model-based estimate of the mean of Y in the full population based on that underlying pattern mixture model. So that estimate of the mean of Y in the full population isn't going to be a function in part of that phi that defines the dependence of selection on your dependent variable of interest and your predictor variables indicated by X. Okay, so we interpret this as the bias in the non-probability sample proportion relative to the overall population proportion. It's simply a difference in proportions. That's all this boils down to. And again, you can find more of the technical details in this paper by Andridge and colleagues in 2019. Okay. Some additional remarks here just in general about computing these estimates of bias. Basically, there's an issue here that we're not doing true maximum likelihood estimation. We're doing a modified form of maximum likelihood estimation. So we use there's what's called a two-step approach, and a lot of this has to do with the latent variable U that we're using in this particular framework. Basically, we just want to make sure that the estimate of the mean of Y in the non-probability sample is equal to the actual mean of the Y's in the non-probability sample once we use this underlying latent variable. So there's kind of a constraint on the estimation. We want to make sure that the second bullet point holds here for this to make sense in the end. And again, as I mentioned earlier, we can apply a fully Bayesian approach for forming credible intervals for this measure of unadjusted bias for proportions. So we can actually make inference about the amount of bias and a range of plausible values for that bias in a given estimate in practice. We have generally recommended using like a range of values of phi that kind of covers the full range between 0 and 1, and also using kind of a midpoint to get a sense of the full range of possible values of MUBP when you're thinking about, again, a sensitivity analysis, or just taking that Bayesian approach where you start with draws of phi because you don't really know what phi is in practice. It's again, a sensitivity parameter. So as a reminder, functions to calculate the MUBP will require microdata from the non-probability sample. We need to get estimates from the probit model. Okay, so we need to actually fit that model in the first place. And again, we also need to have the covariances of the covariate Z, both at the population level and based on the selected sample. That's just a side effect of using this kind of latent variable formulation for the binary variable of interest. So, but we can get that information from the population or for the selected sample. It's easy to come up with those. Okay, so for this to work, we need those covariate Z to be good predictors of Y. When we're thinking about a model for Y in the selected sample, we want to make sure that we have, for example, good predictors of COVID vaccine uptake for this to be effective. We also need that population level aggregate data for the covariate Z. Again, means, variances, covariances, whether we're using just strict maximum likelihood or a Bayesian approach, either way, we need that aggregate information, and it can come from a large probability sample. We also need a clearly defined target population. Who is the population that we're really talking about? Because that's going to dictate what population source we use to come up with those aggregates on the predictor variable Z. So like an easy scenario would be where the target population is all US adults. Stable population, we have a good idea what that population looks like sociodemographically. A harder scenario would be like if you call your target population likely voters. Like in my second example today, that's a dynamic population, always changing by the day. Very hard to track down a good source of population information about such a population. So, but we do need to have a definition to start with so we can find the right source of population information on that group. Okay, So the example that I want to focus on the time that we have is on estimating the proportion vaccinated for COVID-19 based on the Census Household Pulse Survey. Okay, so I'm going to see a little bit more about that here. So this is data from the Census Household Pulse Survey. Some of you may have been part of this. You might remember getting a text message about a given household pulse survey that the census was conducting. My colleague Rebecca Andridge wrote a paper in the Journal of the Royal Statistical Society that looked at the use of these new measures of selection bias like the MUBP to estimate bias and estimated proportions of COVID-19 vaccine uptake based on the census HPS. So our dependent variable of interest is a binary indicator. Have you been vaccinated for COVID-19 or not? Simple 1-0 variable. We're interested in that proportion and estimating it based on the selected sample. So the non-probability sample is this Census Household Pulse Survey, and the data specifically are coming from wave or week 29 of this pulse survey. This was between April 28th and May 10th of 2021. The goal was to estimate the proportion of adults in the US with at least one dose of a COVID-19 vaccine. And again, this time period corresponds where vaccines were available to all adults for that entire month. So at that point in time, everybody had access to these vaccines. The concern is that unvaccinated individuals may be less likely to participate in a study about the COVID-19 pandemic. So again, this could be a source of non-ignorable selection, and we need to come up with measures that would correct for that. Okay. So we consider this a non-probability sample. The APOR response rate 1 was 7.5% to the household pulse survey. So very low response rate, but the resulting respondent sample was 78,467. So you look at this and you say 7.5% response rate, but huge data set. And we ask the question, does big data mean less bias? And this is the paradox everybody's struggling with. If we have 78,000 people, we'd love to have that in every survey. We're guaranteed to get a good estimate, right? Not in the slightest. And that's one of the big messages here, okay? So based on this sample, we were interested in COVID-19 vaccination status. It was missing for a small fraction of the responding sample that we can assume were not vaccinated, but we'll set that aside for now. The covariates that were available for use are basic sociodemographics, sex, age, education, race, ethnicity, and the state where you have residence. And Census did actually create final survey weights for the household pulse survey. So weights were available, which ostensibly should have been correcting for selection bias. But survey weighting assumes ignorable selection. That's the key here, okay? So weights will not fix everything if in fact there's a non-ignorable selection mechanism operating. And that was the key point, and that's part of our analysis, is to compare and contrast the weighted and unweighted estimates with these adjusted estimates, allowing for non-ignorable selection. Okay, so we're going to evaluate the unweighted estimate of the percentage vaccinated, the weighted estimate of the percentage vaccinated, the MUBP index of selection bias. Okay, what are the estimates of the selection bias in this proportion? And then the MUBP adjusted estimate of the percentage vaccinated. Okay, and remember that MUBP is just the bias in the unweighted estimate from your selected sample, from the non-probability sample, in this case being the household pulse survey. Okay, so our target population in this case is all adults age 18 plus, relatively stable, well-defined. We have access to population level covariate summary statistics for those sociodemographics. Those were obtained in this particular case from the 2019 ACS, the American Community Survey. The covariates were limited to demographic information, like I said, but other studies have shown that these demographics in particular have moderate associations with COVID-19 vaccine acceptance. So we might expect a proxy based on the selected sample to have a reasonable correlation with the actual COVID-19 indicators. Now, how can we evaluate how well we're doing? We have the benchmark truth for vaccine uptake. So this was compiled by the CDC. You can see the link where we downloaded this here, and it includes any retroactive corrections to that estimated proportion that have received at least one dose. And the true proportion that was vaccinated as of May 10th, 2021 was 61.4%. So that's our target. That's our benchmark. That's what we know to be the truth. And we're going to see how well these different adjustments for selection bias do to get there. Just as a spoiler, the HPS estimates were very, very badly biased, and the weights did not help. Okay, again, because they assume ignorable selection. So the question becomes, can the MUBP correctly detect and and the direction and the magnitude of the bias. Okay, and if we take that MUBP measure and we adjust the unweighted estimate, are we approaching the benchmark truth? Okay, so that's what we want to look at. So here's our roadmap for the example. And again, with the time that we have, I'll walk through how to do this within R. You can take a look at the R Markdown files at the website that shows the materials for this webinar. We're going to start by calculating estimates based on the selected sample, using the HPS data to get both the unweighted and weighted estimates. That's where most people are stopping in practice, is step one. I have weights, I'll compute a weighted estimate, I'll rate it up. Okay. Step two, get summary statistics for the non-selected sample. These, again, we're going to get estimates of means, variances, and covariances from the ACS as a source of information about the population. We're going to calculate that MUBP index as a function of phi. We'll use Bayesian estimation, and we'll just use maximum likelihood point estimates at selected values of phi. We're also going to check the strength of the proxy. Okay, look at that biserial correlation of the proxy variable X with the latent variable U. Okay. Finally, we'll calculate an adjusted estimate of this proportion based on the measure of unadjusted bias for proportions. Okay, so we're going to take that measure and use it to adjust the unweighted estimate. Okay? And we're also going to be Bayesian in nature in the way that we do that. The software I'm going to show you does all that for you. Okay, so I'm going to flip now to our studio. And again, the markdown file that I have open here is available with the materials for the webinar today. Okay, so I'm just going to go through these different steps here. Start by loading some essential libraries, including the tidyverse and the survey package here for doing our estimation. Step one, we're going to compute estimates from that selected HPS sample. Okay, so the first thing we're going to do is prepare the data. We're just creating binary indicators for all those covariates to use as predictors, because we also want, remember, those population estimates of the means, variances, and covariances. So after I read in the household pulse survey data, which again, I'm happy to share, if anybody would like to work with this on their own, I'm just creating these binary indicators for each of the different covariates here. All right, so we see there's 78,467 respondents in this particular data set here. Now we're going to calculate unweighted and weighted estimates. So I'm going to do that using the survey package within R, starting with unweighted estimates. So I'm going to ignore the weights that were available in the HPS data set and calculate the unweighted estimate in the confidence interval. So I go ahead and run that here. And you see that the unweighted estimate of the proportion vaccinated is 82.3 or 0.823. Okay, nowhere close to what the truth was. Far positive bias. Okay, that's based again on 78,000 observations. So shouldn't we get the right estimate? This is the big data paradox. We have 78,000 observations that are giving us an estimate that's biased by 20 percentage points. Okay, and this is the problem. Okay. Next, maybe the weights will help. Okay, we're going to look at the weighted estimate, create a new survey design object using those HPS weights, recompute that weighted estimate and a 95% confidence interval. Now the weighted estimate of the proportion is 0.741. Okay, so we've reduced some of that positive bias. We're moving in the right direction, but we're still not close. And at the same time, because we have such a big data set, that 95% confidence interval is super narrow. Okay, so we have a biased estimate with very little variance, but we're way off. Okay, this is the issue with big data. Okay, so let's go into those next steps. We get the summary statistics for that non-selected sample. This data set is available as well. This is where you're getting those means, variances, and covariances on each of these binary indicators for the different covariates. Okay, so what you see here is a big matrix of means, variances, and covariances. And we can extract all that information from this matrix for the sake of the function that I'm about to use. So that's what this code is doing, is just pulling out those means, variances, and covariances. Okay, we're going to set the size of the non-selected sample to about 250 million. That's just an estimate based on the size of that adult population. That number itself is not important, not going to have a huge impact on your estimates. We're just using a very ballpark estimate for that population size. Okay, now key point here, these are the MUBP functions that are available up on GitHub, making it possible to compute these particular measures. So I'm going to source both of these functions here that allow us to do the Bayesian analysis and lay out the maximum likelihood estimates as well to be able to compute these measures of selection bias. Okay, and I mentioned what the two important functions are here. Okay, next we're going to do the Bayesian estimation of the MUBP. Okay, so we're going to read in our key dependent variable. We're going to fit that probit model to the selected sample. That's what this step is doing here. Okay, and we're going to save the information from that fit in a new object here that we can further provide to the Bayesian analysis function. Given that probit model that we fitted, we can look at the strength of the proxy based on those linear predictors for that latent variable U. So I'm going to run that particular estimation step to get that proxy. We see that correlation, the bias-area correlation, about 0.464. So it's a moderate correlation. Maybe not as high as we would have liked, but still it's relatively moderate correlation, suggesting that that proxy has some reasonable strength as an indicator of this variable of interest. Okay. Now that we have all the essential ingredients, and we're going to be Bayesian, so we're going to take draws of phi. We're not starting with particular values of phi. We're going to take draws. I can go ahead and carry out that full Bayesian analysis. For the sake of time, okay, I'm not going to run the full 500 reps just because this takes a long time with the size of this data set. I'm going to change the number of reps here on the fly to be 20. So we're only taking 20 draws of this particular estimate just to give you a sense of what this is going to look like. And again, I'm using information from that probit model fit as input to this overall Bayesian analysis function here. Okay, so I'm going to go ahead and run this. It's going to take a second. Okay, we're going through, again, 20 draws of not just phi, but all the subsequent parameters in that pattern mixture model, all those calculations of the bias. We're doing that over and over again. We're taking draws of that MUBP from its posterior distribution. Okay, so that went pretty quick. We can look at a plot of the measure of unadjusted bias for proportions versus the choice of phi, because remember, we were drawing phi. Not super exciting because we only looked at 20 draws, but you get a basic sense of what's happening. The measure of unadjusted bias for proportions that was drawn is on the y-axis. Phi is on the x-axis here. So you can see what those draws of phi were and what the corresponding draws of the measure of selection bias were. Higher value of phi, more non-ignorable selection, more evidence of bias. Okay, you can see that from this particular plot based on only the 20 draws. So then, because we're Bayesian, I'm taking the median of those draws, and I'm taking the 2.5 and 97.5 percentile of all those draws, those 20 draws, to calculate the median estimate of the measure of selection bias and a 95% credible interval for that measure of selection bias. Now, again, I changed it to 20 draws. Okay, we had 500 before. Based on the 500, the median selection bias was about 0.196, about 0.2. Okay, very close to what we saw in that unweighted estimate relative to the known truth. Okay, here, based on my 20 draws, it's about 0.167. Okay, and again, the difference between the unweighted estimate and the true proportion was about 0.209 in this particular case. We're approaching it, and the 95% interval definitely covers it in this particular case. Okay, we can also calculate directly what those measures of selection bias were based on maximum likelihood estimation, so not being Bayesian, but plugging in values of phi, so choosing 0, 0.5, and 1 in another function that's available here. And if I do that, you can see in the output here, assuming ignorable selection, the bias was about 0.08. The median, here 0.5 for phi, about 0.196, similar to the Bayesian result. Assuming fully non-ignorable selection, you can see the bias is all the way up to about 0.47 based on the proxy variable that we're actually using. So we see that, again, that choice of 0.5 for phi looks like what might actually be happening here. Selection is kind of a mix of the actual variable of interest and the auxiliary information. That estimate of the selection bias 0.196, very close to what the actual selection bias in the unweighted estimate was. Okay. Now, step 4, we can use those Bayesian draws of the MUBP to generate an MUBP adjusted proportion. Okay, so we actually adjust our unweighted estimate. Now we can go back and we find that that adjusted estimate is about 0.656 with the 95% credible interval that you see here. I only took 20 draws, so it's pretty wide, okay? But you see we're definitely approaching that 61.4% in terms of our adjusted estimate. And this is getting us much closer than the unweighted or the weighted estimate overall, okay? So I'm going to flip back to the slides just to kind of summarize what we were finding here. And this picture shows all 500 draws, what that relationship between phi and MUBP would look like, and just kind of summarizes what we were finding overall. the unweighted, design-based, and then the MUBP adjusted estimates, in addition to their 95% confidence intervals, we're really correcting most of the bias with this adjustment, allowing for non-ignorable selection. Okay, that's really the key message here. Now, proxy was moderate. What I'm not going to show you, given our time, in the second example, is when you have a much stronger proxy, in the case of political polling, okay, that 95% credible interval for the adjusted estimate can become much narrower. Okay, and that's the key point. We can get a more precise estimate of that adjustment with stronger proxy, stronger predictors of the variable that we're actually interested in combination with allowing for non-ignorable selection. So there is this second example here of from 2020, the presidential pre-election polling. I know we're right in the middle of that right now, so it's very highly relevant to what we're talking about. And this just kind of summarizes what you find if you walk through this other example. You can see the unweighted estimate of the proportion in Wisconsin who would have said they voted for Trump, the weighted estimate based on the poll that was selected here, and then the MUBP adjusted estimate, which again corrects much of the negative bias. That was a big problem in the state of Wisconsin for polling. The actual proportion that voted for Trump there was 0.4882. You can see what the adjusted estimate looks like based on a much stronger proxy and a much narrower credible interval. Okay, so that's what that second example is walking through, with much the same code and the same kinds of data sources. So just to kind of wrap up here, and hopefully we'll still have some time for questions. A checklist of what you need to carry out these measures. And again, I'm happy to correspond about the use of this code after the webinar is over. You need all the relevant R functions and packages that I was just highlighting in that R markdown file. You do need to find a source of informative auxiliary information that's in common to your selected sample and from your population data source that can usefully predict your key variable of interest. And again, you remember, this is conditional on the other key predictors for the regression. Okay, so we need to make sure we find important correlates of your variable of interest that were measured in your selected sample and available at the population level. You need good estimates of means, variances, and covariances for these auxiliary variables in the target population. In my experience, that's been the hardest step with using these measures, is trying to find that good population source where you can get that good common aggregate information. And again, I would advocate for a Bayesian mindset because we don't really know anything about phi. So taking draws of phi rather than assuming phi is equal to some value. If you are to pick a value of phi, 0.5 seems like it's worked very well in a lot of different applications. So something to think about. Okay, just some additional comments here that are some common questions that arise. I'm not going to touch on those in great detail, but at the ends of the slides, I have a list of all the references that are talking about these models, the development of these different measures that I've been hinting at here. So you can take a look at these, and I'm happy to share any of these with you if you'd like to take a look. I also want to acknowledge that the development of these measures and the software that's implementing them was supported by 2 grants from NIH, an R21 to me, and R03 to Rebecca. So we're thankful for support that allowed us to do the work on these measures. So. Okay, so I think I'll stop there. And again, hopefully we'll have a little bit of time for questions. I know it's kind of a whirlwind introduction to these measures, but I think taking a look at the R markdown files will make things a little bit more concrete. And again, you can consult some of these papers for the statistical and mathematical details. So thank you.
So just to get, so first I just want to thank you, Brady, for this great presentation. I know we are running a little bit low on time, but I think we have time for just a question or two. And so if folks want to, you can either raise your hand and we can call on you, or if you want to just throw them into the chat, I'm happy to read them out. While we're waiting, I guess I can ask one question to you, Brady. So kind of the difference between, the Bayesian approach and kind of the maximum likelihood approach, you're able to, from the Bayesian approach, take, those posterior draws. Can you talk a little bit about how, like, the uncertainty, is propagated in the, when you're taking, say, the maximum likelihood approach, or how, how that factors into it?
That's the thing about the maximum likelihood approach. It's not, right?
Okay.
So when I ran those analyses in the maximum likelihood approach, like, I'll just go back here real quick. You're just getting a single point estimate of what that bias is for each choice of phi. So like when I said phi was 0, the maximum likelihood estimate of what that bias was 0.08. I'm not getting a standard error. I'm not getting a confidence interval. I'm just getting that point estimate. So one thing we recommend is that if you don't want to be Bayesian, you could treat the estimate of the bias at 0.5 as like your point estimate or your midpoint, and then use the 0 phi value and the 1 phi value as kind of your limits. Not a confidence interval by definition, but just kind of a range of
I
plausible
see.
values for that bias in the maximum likelihood approach. That's why I like the Bayesian approach, because you can actually make inference about both the bias and the adjusted estimate. So,
Gotcha. No, thank you. That makes a lot of sense.
yep.
It looks like we have a question in the chat from Craig. He asks, what are the covariates in the polling example, and would they likely be the same in this cycle, or can we only know the relevant covariates in retrospect?
Great question. I will bring those up here. All right, so in the polling example, our selected sample from the poll was about 803 likely voters. And these were all the covariates that we considered. So sex, age, education, race, ethnicity, political ideology, and party identification. And what made this proxy stronger than the proxy in the case of the HPS example was those last two guys. Political ideology and party identification, strong predictors of whether or not you're going to vote for candidate Trump. Okay, so that made this proxy much stronger. Like if I show here, maybe I didn't have it on the summary slide, but the proxy was approaching like 0.8 in terms of strength. So those last two predictors, highly relevant and probably would still be relevant for this cycle. But again, there's this constant hullabaloo, like what were pollsters like, why am I missing? What are we missing right now? What's going on? Everybody's still just using weights. We keep trying to say, you're not allowing for non-ignorable selection, this partisan non-response bias. Weights will not help you. Everybody's like, well, let's use this to weight, or let's use this to weight, or why don't we use this to weight? None of it's going to help if there's a non-ignorable selection mechanism. That's the point. So yes, these covariates might be useful in this case, but we also have to allow for the possibility of non-ignorable selection. And that's what standard weighted estimates like we're reading about in the paper every day are completely missing. So.
Perfect. Well, I think with that, since we're already a couple minutes over, but first off, we kept most of the folks here, so I think that speaks volumes for just how interesting this is. I want to thank you again, Brady, for talking about this.
Yeah.
And as Megan has mentioned in the chat, the recording of today's presentation will be shared on YouTube. There will be a little bit of a delay, so probably in the next few days to a week. And then she's also added the link to the code and slides from today's presentation. So with that, thank you guys so much, and hope you enjoy the rest of your afternoon.
Yep. Thanks, everybody. Appreciate it.